All right. Hi, I'm Louisa. I will be the MC for Sharon's talk. Uh, Sharon Xia is a principal PM manager at Microsoft, and she will be doing a talk today on detecting emerging cyber threats using machine learning. So, without further ado, let's get started.
Thank you, Luisa, for the introduction. Hey, everybody. I'm so excited today, and there are so many great talks. Um, so let's dive in right into my topic, our topic today, detecting emerging threats. You know, on this slide, I showed 3 cyber attacks in 2021. You probably all heard about SolarWinds, right? And this attack had not been noticed for 15 months. The impact of the SolarWinds is massive. 18,000 businesses were infected by the malware, and hundreds of software were affected. So attack groups like Novalium, a Russian hacking group, kept attacking more enterprises using the mutated version of SolarWinds towards even, end of 2021, after 1 year, the original SolarWinds attack was discovered. Um, so, the like this one, malware Zeus. It's a fascinating, you can say, story. It's even more like a Hollywood movie. So it started in 2007 and have gone through many, many mutations. And the creator created different versions and sold the source code in the black market. And then the copycats created a lots of versions. And it evolves from a simple malware to botnets and to malware as a service. And one of the copycat, they bought the original source code and created spy that have stolen millions of dollars from individuals and banks. Um, FBI and many security companies, including Microsoft, tried several times and tried to crack down this, specific family of malware. Unfortunately, still as of today, the variation of it is still going on, and the original creator is still at large. So, so, so why the cyber? With this is really like a cyber war with attackers and the defenders are competing. The intelligence, everything, the resources, lots of things. And we learned that ransomware, actually they operating those as a business. They have tech supporters, they have sales organizations. This is just, it's a constant war at this time. And when we look at the landscape, right, as an organization or as an enterprise, we are facing incredible difficult tasks to protect the entire expanded digital estate. You know, uh, the move to the cloud and to a mobile workforce has pushed the border of enterprise estate from beyond the physical network in the old days, right? Data, users, machines, systems are everywhere. And meanwhile, the frequency and the sophistication of attacks are ever growing. So regardless of the size of the organization or your individual, you are a target today. And when we look at the data scale, right, this is just a example of the data like we have access. We typically keep tagging on they are in trillions and billions signals across world. It's just literally a universe. Um, for that. And with this kind of the scale, traditional rule-based detections and a manual response cannot handle those kind of scale. And the ever-changing attack techniques, the mutations we talked about, and the AI-driven machine learning speed attacks. So using AI and the machine learning in security is not only a market trend right now, but also a necessity to combat the modern cyber attacks. So in this talk, we will discuss two case studies. Both are used in Microsoft security products today in production. So the first use case study is a geo-logging anomaly detection. The problem statement is detect anomalous Azure Active Directory logins from unusual geographic locations. So the hypothesis is a login is anomalous if the distance between the places is unreachable. For example, Sharon logged in at 8 a.m. from Redmond, and then we see another Sharon log in at 8:10 from New York. So it's not reachable between Seattle, Redmond, and New York within 10 minutes, right? So this is anomalous logging for us. So in the history, we use the rules and heuristics, and there are lots of false positives because various reasons. So the rules and heuristic based detection, the false positive rate was 28%, which is pretty good from overall detection side, but it's not good enough because you see in the previous slide, in the cloud, we're dealing with trillions of logins every day. 28% from trillions logins is still too much to handle for anybody to do analysis. So what we have done is this slide just give you a high level technical overview of it. What we have done is we capture 45 days login data and capture the users and the locations as well as the ISPs, internet service providers, their, the proxy data as they are logging from. And we also mapped user similarity matrix using spectral clustering. Here in the middle, you can see user 1 and user 2 are very similar. We are, so the use case is Sharon may be usually logging from Redmond. Occasionally, I travel to Boston or somewhere like San Francisco. But I rarely, for example, go to Africa, right? Or never went to Africa before. So Africa is an unusual location for me. But is Boston an unusual location? And all reachability, and we want to also compare the peers, behavior in this scenario. And for each user, we also build this reachability score to different locations using random walk algorithm on the previously computed matrix. So user 3, for example, is a Bayview based. Her reachability to Bayview has highest score, and since she is a Microsoft employee, so in the Verizon Boston office location has the lowest score. This just give you an idea, how we use machine learning and to reduce those false positives. So to highlight, our model is trained in regular intervals with about 800 gigabytes per day data within hours. And our classification is running through streaming mode, so we can score these events and identify these impossible travel, anomalous location logging in milliseconds. And here is an example, we successfully identified a suspicious logging from Lagos. So this is confirmed is, some user attack use a compromised account to log in from an unusual location. And with these machine learning algorithms, and the detection becomes, the true positive, false positive rates basically drop to below 0.1%. It's have a 28 times points improvement. So this is how effective we use machine learning to detect suspicious logging from unusual locations. And this use case, you can tell, we just use one data to source, like to identify unusual logins. And in the typical enterprise, there are billions and trillions of activity logs, right? After user login, user do something, right? And there are network connections. So it's impossible to sift through all these billions and trillions events manually. Advanced attacks usually start with engineering, right? Like phishing to compromise the user account. Then use the compromised user account to log in. Some logging may be legit, right? Not even in an unusual location, right? And then after they log in, they get a foothold in the system, meaning, they look around, they might install, malware and without your notification. No, and then they start to, all the exploration and plant, attacking plan, like the SolarWinds. It took, they've been in the system for 15 months until they were discovered, right? So you probably know that there are effective machine learning algorithms such as auto-encoding can detect anomalies effectively, individual sources like our geologging location, detections, right? But most of anomalous behaviors, some even more stealthier, can't even be detected by anomalous behaviors, are not necessarily, malicious. Unusual logging, maybe there is a mistake about the ISP, the proxy change, all these. There are lots of false positives. So this slide shows average data scale in a month for our fusion process. So let me define the fusion. Fusion is one of the machine learning technology we use. It uses multiple machine learning algorithms and designed in concert with our security researchers to automatically detect sophisticated and emerging threats by identifying combinations of anomalous behavior and suspicious activities across various stages of attack chain and various signals. So, so this is, how fusion works. The input are anomalous signals, and then, it forms a graph, and then it does attack pattern matching by, comparing the attack patterns in the knowledge pool, and then it goes the expansion stage and the scoring stage, and it create incidents. And we will go through each steps in the next few slides. And due to the time constraint, we're not going to talk about how we use machine learning to generate emerging attack patterns. So this is another probably 20 minutes talk about how to use that. But we assume, we do have an algorithm and generating emerging attack patterns from known patterns and from different IOC, the threat intelligence we have in the system, and feed that into the whole ML algorithm to generate attack patterns. And then let's look at the hyperconnected graph. So the fusion as a ML framework and has multiple algorithms. First one is using graph-based neural network to build and updating continuously updating the graph, right? Typically, we do multi-million of anomalous signals in the custom workspace. And in the graph, you can see it's a hyper-connected graph. The nodes represents the entities like users, host, IP address, cloud resource ID, etc., right? And activities may be anomalous logging, running a command line, a PowerShell script, or inbound egress, ingress, network connectivities. And the edge of the graph are representing the relationship between the nodes. So, when you look at this graph, it's just a huge graph, hyper-connected. And then the next step is how can we find all these associations, find the attacks in the, basically among these hyper-connected graph. So like I said, Fusion keeps a large set of attack patterns in the knowledge pool, including known attack pattern and ML generated attack patterns, right? So then this step is Fusion goes through finds the matches in this hyperconnected graph. Those identified matches are called subgraphs. And this step reduced millions of the anomalous signals nodes to a smaller set of subgraphs representing the possible attacks. On this example, for example, on the three attack patterns are matched, and in the top, like we have 4 nodes, right? And the 3 edges, meaning there are 4 entities and 3, relationships between those edges. So basically, these represent the TTPs, tactics, techniques, and the procedures in these attack patterns. So once we identified attack pattern match, then the next step is doing the subgraph expansion. And during this expansion phase, a probabilistic kill chain model that uses random walk is applied to determine the viable attack passes in the graph from the matching patterns. And the model runs multiple times to simulate all the different possible attack passes. So after finding all possible attack passes, Fusion aggregates the weights across multiple runs and apply a threshold at this subgraph level. So in this case, to drop the subgraphs that represent unlikely attack patterns. So this is results, you can see the green nodes on the graph, right? All these dots and edges of green are expanded possible attack passes around this attack pattern. So then the final step of this is Fusion uses key nearest neighbors algorithm KNN to calculate the kill chain reachability of an attack and identifies the nodes that have the highest relevance in a real attack. So this also involves, consulting the attack database, the knowledge pool, and other dynamic context enrichment information. In this example here, all the colored nodes, orange, yellow, green, are relevant to an attack. After the scoring round, Fusion only surfaced the nodes that have the highest relevance entities and activities. So in the incident to security analyst. So this basically, we drop the, you see the green nodes and only surface the yellow and orange nodes to the security analyst to further reduce the noise, and so they can focus on those most relevant entities like users or host IP address, and the most relevant signals means activities, so they can do the investigation here. So that's to give you an example of a command and a control thread we detected in a customer environment. The attack started, detecting the distributed password cranking attempt in Azure Active Directory. And then, we see associated anomalous Azure AD sign-in session. And then there are logging using, over the past hash. And then we see some suspicious PowerShell command line, network beaconing pattern, and traffic detect to the IP address from, the blocking list, but it's not blocked on the firewall, etc. And they all related to, a user, a dedicated host, some suspicious IPs. So we surfaced this obvious, ongoing detections. You can see the timeline here, right? It's over more than about 24 hours, all these activities, and alerted the customer. And, the customer is able to stop the attack before any damage to the business happens. I saw a question is how frequently is the model being trained in case of study one? We train the model every 12 hours. All right, so the two use cases we looked at here are all linked to, about detecting the threats, right? And ML can be applied to, other areas like hunting, like actively hunting for threats, or in the area of security orchestration, automation, and response, auto remediation. And so, for example, the ML model can learn, for a particular threat, the history, how, this threat was mitigated before, and give recommendations to speed up remediation in that area. So there are many areas we can apply AI and ML in security to help our, defenders to be, combat with those advanced attacks. So here are the resources, a few articles that, have deep dive, for example, the fusion I talked about, it's a very detailed blog about this. And there are other technical blogs. You can talk about how we, provide customizable MLs, basically enable customers to configure the features and the threshold on the building models. The model is black box to customers, but they can, tweak the features and tweak the threshold to improve the fidelity of a model in their environment. And we are also doing research. The last one is about the attacks to machine learning algorithms. There are like a model invasion, model poisoning, various model stealing, and various attacks that are specific to machine learning algorithms. So this is just one article. We, our team also do this kind of research and see how can we mitigate or detect those special attacks to the machine learning algorithms. And the last shameless plug is we are hiring. So if you're interested, reach out to me. That's all the presentation. I assume the video, the slides will be shared after the conference. And any questions